Got it. Okay. We're live streaming. That's the good part. Looks good. Cool. Can you email me the Zoom link with the past everything so that I can click? I may need to use my iPad. That's why. Okay. Thanks. No. Welcome, everyone. I think this is the effect of the before the Easter break. We have fewer people, but it's still pretty consistent, so that's good. So before the Easter break, we're going to cover precise exceptions, which is a critical aspect of designing a von Neumann machine, actually. And then we're going to maybe start out-of-order execution. At least we're going to lay the ground for out-of-order execution, because what we're going to discuss in this lecture is going to be important for out-of-order execution. We're going to discuss register renaming, for example. Before I go on, I would like to remind you that there's a feedback form some of your colleagues have prepared. Please fill that out. I would like to see all the feedback. If you're satisfied with the course, just say, I'm happy. If you're not satisfied, discuss what you like and what you don't like. This feedback is very useful so that we can adapt the course this year and in the future also. So please fill the form. There are, I think, 550 students registered for the class. And I don't want to get feedback from 100 only. That's not very representative, right? 100 out of 550, if you do the calculation, that's even less than 20%. Ideally, the participation should be more than 90%, right? That's how systems normally work, right? This is why many democracies in the world don't work, because they're not democracies and people don't participate, right? You look at the voting registrations, basically people who vote, 50%. Okay, and what fraction of them are really informed? Maybe 2%. Okay, so I don't want to run into the same situation basically over here. So please participate. Okay, this is where we are actually. We're going to finish pipelining with handling precise exceptions. As I said, this is a very important topic. And we're going to leapfrog into out-of-order execution in this lecture. And we're going to talk about out-of-order execution actually, hopefully, in the second part of this lecture. But that depends on how much progress we make in the precise exceptions part. And these are your readings. I would suggest doing the readings if you're not really fully understanding something. Readings are actually very helpful. I actually cover some of the readings. Some of the things I cover are not from the readings, but readings actually explain things in more detail and also at your speed, right? So next week, we're going to cover these readings, as you will see. And as I said, this is going to be an important survey paper, overview paper that covers the microarchitecture of superscalar and out-of-order processors, essentially all processors that are out there today. Okay, but before we go into that, actually, this reading covers interrupt and exception handling as well. So that reading is still relevant. When you do it, you will reinforce the concepts that we covered today. Okay, so this is the title of this first part of this lecture. How do we maintain precise exceptions in pipelining? Meaning, how do we preserve sequential semantics? And you may say that, oh, we already covered this, right? You said we discussed that every instruction writes its result into the register file at the end of the pipeline, meaning write back stage. Yes, that's true, actually. We're going to kind of deconstruct that today with some notion that I will introduce, which is the notion of multi-cycle execution. Basically, the pipeline that we saw was a very simple pipeline. It's 5 stages, right? It's actually very basics, I would say. If you're building that, that's good. You're learning. That's great. But in real machines, the pipeline is actually a lot more complicated. Basically, what this slide is saying is absolutely true in real machines. Not all instructions take the same amount of time. I don't know why there's a 4. I'm going to do the online error correction. Take an exception. Though this is an exception, as you can see, I found an error. And I corrected the error. And I returned back to execution. This is an exceptional condition, right? That's exactly what happens in machines also. Machines is executing some instructions. Some problem happens. You fix the problem, go back to the execution of instructions. So that's basically what we're going to talk about today. But to understand this, really, why this is a problem in a von Neumann, in a pipeline machine. Okay, that's not what I want. I want to get rid of this one. Okay. We really need to understand this notion of multi-cycle execution. Basically, not all instructions take the same amount of time in the execute stage of the pipeline. So far, we've assumed 1 cycle execution, right? We're going to deconstruct that. Basically, the idea is many instructions take different amount of cycles. For example, an add instruction may take only 1 cycle because it's a simple addition. A divide instruction may take 60 cycles. A floating point divide instruction may take 80 cycles. A load instruction may take 100 cycles because it needs to go to memory because the data is not on the on-chip memory, as we will discuss later on in the lectures. So basically, a real pipeline today looks something like this. Even this is simplification, but the basic idea is there. You fetch, decode, and then depending on the type of the instruction, you go to different execution units, different functional units. One of them can be an addition unit, another can be a multiplication unit, another can be a division unit, floating point multiplication unit, load unit, store unit, who knows what else, right? And load unit, store unit may be different also depending on where the data is. So this is really what a real machine looks like. And if you look at this, then you have a problem, right, with this picture. Because you fetch and decode instructions in order, send them into the execution units in order, and one instruction takes, let's say, 60 cycles to complete. Another instruction that comes after it takes 1 cycle to complete. So what do you do in the write-back stage, basically? So these execution units can be pipelined or not pipelined. It's not as important. The important thing is they take 60 cycles. Pipelining, of course, pipelining this, as I show you over here, actually is better for throughput. But basically, what this sort of structure allows you to do is you can let some independent instructions start execution on a different functional unit before a previous long latency instruction finishes execution. For example, let's say we start a floating point multiply, which is going to take, in this particular case, 8 cycles. We execute it. It's going to finish 8 cycles later. In the next cycle, we can start an addition that's completely independent. It doesn't need to stall because it doesn't need any results from the pipeline. So it starts. But it finishes in 1 cycle. So what do you do in the write-back stage then? Who goes to the write-back stage first? Right? That's the key question over here. If you have these instructions that have different latencies, how do you write the results back to the architectural state? We're going to discuss some problems related to it, and we're going to discuss why it's important also. Okay, so that's why there's a question mark, because we're going to deal with that part of the pipeline today. Okay, so let me motivate the problem a little bit more. So basically, now we have a different pipeline, slightly different. Instructions can take different number of cycles in execute stage. You can see an example over here. And you can see that I have an integer addition versus integer division. Division normally takes much longer cycles. 8 is actually pretty good division, I would say, depending on the clock cycle time, of course. But you can see that this is one way of handling the instructions. So divide instruction gets fetched, gets decoded, starts executing in this cycle. In the same cycle, the second add instruction, which is independent, gets decoded. It starts executing in the next cycle. In the next cycle, some independent instructions start executing. So let's concern ourselves with just this portion first. Divide instruction executes, and after 8 cycles, it finishes execution and writes its result back in cycle, I don't know, 1, 2, I think this is 11, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, cycle 11 over here. But somehow we designed the machine such that the second instruction that comes sequentially after the division goes through the machine, executes in 1 cycle, and writes its result back to the register file in cycle 4, or 5 in this case. Next instruction, which I'm not showing you over here, independent, assume that it's write its result back in cycle 6. Next instruction, cycle 7. Next instruction is a divide. Again, pipeline is being filled sequentially, but instructions are kind of writing their results out of order, right? So you can see that by the time this division instruction writes its result, 1, 2, 3, 4, 5 later instructions have already updated the register file, right, with their results. It could be memory also, but keep things simple right now. Let's talk about registers. So maybe I'll ask you the question. What's wrong with this picture in a von Neumann architecture, if anything? Anybody? It has to do something with these write backs, right? Any guesses? Yes, please. Exactly. That violates the sequential instruction processing principle, right? Basically, sequential semantics of the ISA is not preserved. That's a legalistic way of thinking about it, clearly, because you're violating the contract, right? And that's absolutely a problem, right? Because the contract is there for a reason, as we will discuss, because the programmer relies on it, right? Basically, this division instruction should have written its result before any later instruction, according to von Neumann semantics. Right. We said that the sequential instruction processing is good for debugging. We'll talk about that also. Okay, let's assume that. But why could this be a problem? Because this division may not actually work correctly, right? So, for example, the division is chugging along in the execute stages, and you figure out that the machine figures out that it's a divide by zero, basically. Whatever you're dividing by is the register 2 in this particular case. If you're dividing register 1 by register 2 happens to be 0. You figure this out over here, let's say, meaning that you should not have even executed this division, right? That's something wrong. You don't know what the result would be divided by 0, right? This can happen in a real system, and you don't know the result. It's called an exceptional condition. That's why we're going to talk about exceptions. You don't know what the result would be, meaning that somebody needs to do something about this. But you already written the results of these instructions into the register file. So how is the programmer going to figure out what happened? Right. Now the programmer, let's say you're the programmer, somehow the machine stops because there's a divide by 0 exception. You go and you try to inspect what's happened. You would expect from a von Neumann architecture that these writes did not take place. And these writes did not take place. Whenever you look at the register file, whenever you actually inspect the contents of the register file, which is exposed to you because you can actually do that, you should not see updates from any later instruction in program order that comes after divide. And you should also expect that every instruction before divide must have finished and updated the register file in memory. That's the expectation. That's what you expect so that you're able to debug this program, right? Otherwise, it's very difficult to debug this program. How do you go and figure out like what the values of these registers were? Yes, please.
How can it be that the first instruction is executing while the divide still using up the execution?
Oh, basically, what I said is that you have multiple execution units, right? The assumption is that you have different execution units for add and divide. Yes. Okay. Okay, good. Okay. So basically, we're going to solve this problem. Hopefully, this is clear to people why this is a problem, right? You cannot debug this easily. I mean, you can debug it because you can do anything if you really know what you're doing, right? But the problem is it's very difficult to figure out what has happened if these instructions already wrote to the register file, because you don't even know how many instructions wrote to the register file also, right? You need to really reverse engineer a lot of things. But see, von Neumann architecture, for a good reason, says for aid debugging says that this no later instruction should have finished. And if your expectation is that way, that's what you should find in the machine. Okay, so just on the lighter end, these exceptions happens in real life also, right? This is when I was actually coming to teach this lecture. This is what happened in real life. This is an exception causing instruction. It couldn't move in the pipeline because something happened over there. It got a power failure or whatever. It couldn't move. And later instructions are delayed. And you need to handle the exception so that you can move, let's say, later instructions. It's not a perfect analogy, but you can see that these exceptional conditions are real in real life also. And other, let's say, instructions are also delayed, as you can see over here. Now you can see this is an exception causing instruction. I'm not making this up because you can see that this instruction or train did not actually go to the station. It's waiting. This is 2 minutes later. This is 3 minutes later. This is 5 minutes later, I guess. It's still there, as you can see. And this is a closer up view, if you want to see that. But finally, the exception is handled and resolved. This is, I don't know, 11 minutes later, but probably it was handled 2 minutes before that. So exception is finally handled, and this instruction is moving. Maybe it got a divide by 0, and the programmer went back and said, oh, okay, maybe I did, there was something wrong in this value. The value should have been fixed. You could actually do that. As a programmer, you can actually catch the exception that's thrown, and then write an exception handling routine that fixes the values in your program potentially, or does something basically, or stops the program if you cannot fix anything. Right? In this particular case, it's clearly fixable if you can make the instruction move, and the instruction finally moved, and somebody handled the instruction and resolved it such that this instruction moved and later instructions also moved. So I like this analogy, but clearly it's not a perfect analogy because it's not a single program. These things are not these trains are not a single program, right? Okay, but basically where the analogy is really the same is you have unplanned changes or interruptions in program execution. Right? You're executing a program, lots of instructions. You have some unplanned thing that happened. You didn't plan it. An instruction did not execute correctly, or the data value was not good enough for the instruction to execute correctly, or someone interrupted the execution. So these two things are actually different. I'm going to differentiate between them, exception and interrupts. Basically, exceptions happen because of internal problems due to the execution of the program. You wrote a program. It's a sequential set of instructions in a von Neumann architecture. And something happens in an instruction. You execute an instruction that's not supposed to be executed, or a data value is wrong. As a result, this is called an exception. It's an exceptional situation in the program. This is going to be important because these two are actually different in terms of how you can potentially handle it. The way you handle it is actually very similar, but there are some differences between exception and interrupts. On the other hand, if there's an external event that happens that needs to be handled by the processor, this is called an interrupt. So this has nothing to do with the program you're executing. Somebody presses the keyboard, for example, and there's a program executing in the processor, and that input to the keyboard has to be handled. And this processor is selected to handle it. So you need to interrupt the program that's already executing and handle that interrupt, meaning external event, and go back to the program afterwards, right? So this is actually interesting to think about because if you think about it, exceptions are very fundamental to the program execution. There's also some philosophy to think about over here because exceptions happen because something wrong went with the program. In a sense, exceptions are not a problem with the von Neumann architecture itself. Exceptions can happen in any architecture. Data flow, if you remember, we discussed data flow. You may have a divide by 0 exception in data flow. But interrupts are a bit weird. In the sense that, why are we interrupting this processor? What if we had tens of thousands of processors, right? And we dedicate one of them just for handling an external event. Then you can get rid of interrupting a process that's executing, right? Potentially. So external events are a little bit different from internal events. Internal events, you have to stop the program, handle it because there's a problem with the program. External events, it's not related to this program. So maybe there are other ways of handling it. So interrupts, therefore, are a very, very von Neumann notion. It comes from the old times where you have a single processor. That's the only thing that can execute things, anything. There's no tens of thousands of processors. So you have to execute an outside external event on this processor. And if this processor happens to be running a program, well, too bad for that program. Get rid of that take it out, execute the interrupt, handle it, and put the program back. So the soul of interrupts are actually very much von Neumann also. But going forward, this may change. With data flow, for example, the notion of the interrupts actually don't mesh well with the data flow architectures because in data flow, remember, everything's a data flow graph. Interrupt comes in, it's actually part of the data flow graph that's executing in the system. So everything in the system is a data flow graph. There's no notion of interrupting in a sense, right? It's just another input to the data flow graph. Okay, I wanted to make this clear because these are two fundamentally different things. But the way they're handled in von Neumann architectures are actually very similar, with some minor differences, let's say. Okay, basically both of them require stopping the current program in a von Neumann architecture, assuming the interrupt is going to be handled by the processor that's executing on that, by the processor that's executing this program. Saving the architectural state of the program. Remember the architectural state, registers, memory, program counter. And handling the exception and interrupt. And to do that, you need to switch to a handler, basically. It's called an exception or interrupt handler. This is a specifically written program or piece of program that is designed to handle a particular exception. If the particular exception is divide by 0, this could be supplied by the programmer, for example. Programmer knows the semantics of their program. At this point, if I get a divide by 0, oh, I know why I got it. So I'm going to do something about it. Maybe I'm not going to divide by 0 at that point. Oh, that 0 is very important to me. I'm going to save it somewhere. I'm going to keep executing, right? Because as a programmer, if you know the semantics of your program, you can actually understand what you need to do when you get a divide by 0 exception. Most programmers don't do that necessarily, but some of them do actually. If you program in Java, for example, normally what you do in an exceptional condition in Java, if you catch an exception that's thrown, potentially by the processor, and you basically handle this exception. If you do a try catch block in Java, that catch block is there to actually catch the exception and do something different from the normal flow of the program. Okay, interrupts are actually very similar. So a keyboard interrupt comes in. Here, you basically go to a handler that executes code to get the data out of the keyboard and puts it into an appropriate place that it needs to go to so that the system actually does something with it, right? Okay, and in the end, if possible and makes sense, you need to return back to the program execution because you interrupted, stop the program, you handle the exception or interrupt, and then you put the program back on the processor and continue executing from where you interrupted the program. But of course, there's an if possible and makes sense over here. Meaning, if there's an exception and the exceptional condition cannot be resolved successfully, then the program may be halted, right? Maybe the solution is to halt the program, say this program cannot continue. If it's an interrupt, if it's like a keyboard interrupt, okay, you handle the keyboard interrupt. It has nothing to do with this program potentially, and then you go back and continue executing the program. That's possible and makes sense. If it's a power failure, the power is running out, and you get an interrupt saying from the battery saying, okay, your computer is going to stop soon. Well, maybe it's not possible to actually put the program back. And if it doesn't make sense, maybe, right? Because your power is running out. How are you going to execute this program, right? So basically, it all depends on the type of the exception and interrupt, how you go back, what you do in the end. Okay, so let's take a look at some examples of these exceptions and interrupts before we go further into how we actually handle this. So some exception examples, remember, these are internal to the program, divide by 0. It could be an overflow. You're building an ALU, for example. You get an overflow, and this overflow has a meaning, right? You cannot represent the value that's a result of your ALU in the number of bits that are allocated to the output. And the programmer needs to potentially do something about it because they may get a wrong value in the end, right? I don't know how many people are familiar with the Y2K bug. You're all probably, okay, year 2000 bug. Okay, it's basically an overflow issue, right? You cannot represent some time beyond the capability of the length of the register that's allocated to it. As a result, you have wrong times in the computers that are not able to represent things. So that's an overflow condition. And if your programs do not handle this overflow correctly, you'll get the wrong dates all over the place. That's why people are very much worried about that Y2K bug, because at that point, things would be overflowing. There are some other examples over here that are even better fit for this, but I'm not going to go through that. So undefined opcode could be another one. You're fetching an instruction, you get an opcode, and it's an opcode that's not supported by the ISA and the hardware. This can happen because something may be corrupt in memory, right? Again, this is an internal condition. General protection, you're trying to access a memory location that you do not have access to. We're going to talk about that, especially the second general protection and page fault when we talk about virtual memory in lecture 25. You don't have access to this place. You're trying to access it. You generate a memory address, and you get an exception saying, oh, you cannot access it. What happens afterwards, right? Page fault is related to virtual memory, so I'm going to skip that. How many people know about page faults over here? Okay, a small fraction. You're going to learn about it in lecture 25. We don't have time to really cover it at this point. Is it because of the other one? Okay, let me try again. How about now? Okay, yeah, something fell. Okay, so page faults, we're going to see that in lecture 25. Basically, there are a lot of exceptional conditions internal to the program. Interrupts are as you can see, right? There's another exceptional condition. Okay, let's see if this is going to work. Okay. So basically, interrupt is you asking me a question, for example, right? That's not, I'm running a process over here. Your process is asking me a question that's interrupting me. That's interrupt, basically. And it's good to do those interrupts, basically. But basically, interrupt examples from a real processor is some I/O device needs service. Keyboard input, video input, microphone input. I don't know. It could be, there's a lot of outside input, outside world interaction today. Another example is system timer expression. This is actually very interesting. For example, there's a timer that can be set by the operating system saying that periodically interrupt the processor because I'm going to perform some maintenance tasks on the processor. What could be a maintenance task? The operating system maybe wants to schedule some other task on the processor. So periodically, every 10 milliseconds, for example, sometimes it's even more frequent, the timer expires, and that timer interrupts the processor, takes out the program out of there, and schedules some handler, interrupt handler, called the timer interrupt handler, where the operating system performs maintenance tasks, saying, okay, I'm going to schedule some other program over here if it wants to. Power failure is a critical interrupt, clearly, as we discussed, right? That's another interrupt going into the processor saying, I need to do something because power, I feel that power is going down. Machine check, there's some error in the machine, I need to handle it. And this may be important for the system. Basically, you can see that these interrupt examples are related to the system. They're external to the process, whereas these exceptions are internal to the process. Okay, any questions? Okay, so let's talk a little bit more about this. So cause, I hope it was clear. The cause is the fundamental difference between exceptions and interrupts. As a result, it's going to dictate the other three differences. So exceptions are internal to the running thread, interrupts are external. This dictates when do you handle the interrupts and exceptions. So normally, exceptions are handled when detected, meaning, especially if you're handling them correctly, like in a von Neumann architecture. You have a instruction, you detect there's an exceptional condition with it, and you know that this instruction is on the correct path. That's what this known to be non-speculative means. You're not going to flush this instruction. Remember the flushing from last lectures. Then you should handle it because you cannot continue the program, right? Because there's something wrong with this instruction, or there's something at least unusual with this instruction. You should resolve that situation before moving on. That's why exceptions are handled immediately almost, when detected, in other words. Interrupts, usually, they're handled when it's convenient. Because, meaning, they have nothing to do with the program that's running. Something is interrupting the processor. So if that something can wait for some time, maybe it should wait for some time. So when it's convenient for this program to get descheduled, handle that interrupt. So you see the difference, hopefully, because exceptions you cannot continue unless you handle it. Interrupts, most interrupts, you don't even need to handle it for some time. Of course, the downside is if you delay the handling of an interrupt, it may take a long time. For example, your keyboard input to arrive on the screen, for example, right? That's one example. So you need to be cautious of the interrupt latency as well. But of course, there are some interrupts that are very high priority, like power failure and machine check. You'd better handle them right away, right? If power failure is going to happen in the next second, you'd better go into a mode where you take out all the processes, all the threads that's running on the processor, and then go into this power failure interrupt handler that basically saves the entire system state so that you don't lose any data, right? This could include saving your state to the solid state drive, right? To make sure that all of your updates are actually persisted in persistent memory. Machine check is another example. Usually what happens is there's some error correction mechanisms that are in different parts of the machine. And one error correction mechanism says, oh, I detect an error. There's a bit flip in memory, for example, for whatever reason. While I'm scrubbing memory, usually sometimes memory gets scrubbed, meaning you check whether the memory has changed without any store actually being executed to change the memory. And this memory controller says, oh, I found an error. And I need to basically interrupt the processor because this could be something really critical, right? You may be under attack because somebody, like a RowHammer attack, if you remember, it could be many different things. It could be that somebody is going to read this erroneous data and use it for some important purpose, right? So basically, this machine check is high priority. So normally it's handled at very high priority, almost immediately. Okay, so that gives me the priority. Again, this is dictated by the cause and when to handle exception and interrupt types. The priority of the exception handler is the process because it's internal to the process. whenever you're handling it, you don't know anything about the system, meaning it's not executed in the context of the system. As I said, the programmer can write the exception handler. Whereas the priority of the interrupt really depends on what kind of interrupt it is, but it's usually the system, meaning it's usually a system level context. For example, the timer interrupt that I discussed. The timer interrupts the processor. And it's the system really actually that needs to do some maintenance tasks. So it's really the context of the operating system, for example, to handle that. Okay, so think about that a little bit. And I think the handling context is very similar to the priority in the end. Okay, but priority also depends. Priority, like basically priority of the interrupt can be very high or very low. But be careful of the interrupt latency. For example, the machine check interrupt and power failure are very high priority interrupts because the system needs to deal with it right away. But a keyboard input or a camera input may not be very high priority because system has some slack in dealing with it. For example, this camera right now is putting a feed into this machine, and there's some slack over there. You don't need to keep interrupting the processes, although there may be better ways of handling the camera, which you can think about. Okay, handling context, I've kind of mentioned this actually. The exceptions handling context is process and interrupts is a system, and I've given you many examples related to this. Okay, any questions? Now that I've laid the ground, let's talk about how to handle these. And we're going to introduce the concept of precise exceptions and interrupts to solve the problem that we saw earlier with the out of order updates of the register file. Basically, the architectural state should be consistent or precise when the exception or interrupt is ready to be handled. And this is really a requirement of the von Neumann architecture. So what does this mean, basically? All previous instructions should be completely retired. I'm not telling you anything new in a sense, actually. We discussed that Neumann architecture dictates sequential processing. I'm going to basically rehash what sequential processing means. For the exception causing instruction, or for the point at which you're handling the interrupt, all previous instructions should be completely retired, and no later instruction should be retired. So what does retired mean? Finished and updated the architectural state. Basically, yeah, this is what I said. Retire is sometimes called commit, sometimes called graduate. I don't like the graduate as much, but committing is finishing in the end and updating the architectural state. Architectural state update is the most important part. Okay, somehow, basically, if you go back to this picture that I showed you earlier, well, there are a lot of pictures in between, so we're going to try to go faster. Okay, if you go back to this picture that I showed you over here, this should not happen. Whenever you're handling an exception over here, all prior instructions to the divide should be finished and update the architectural state, and no later instruction should be finished and update the architectural state. So this picture is basically violating precise exception semantics, meaning these instructions that come later than the divide should have been delayed in updating the architectural state until this point, this point, this point. Okay, so we're going to see that in a little bit. Okay. Okay, so, okay. Any questions on this? Okay, so how do we handle this then? Assuming that this is what we satisfy, what we would like to satisfy, and this is what we'd like to satisfy in a von Neumann architecture. This is how exceptions are handled in pipeline normally. Interrupts are very similar, actually. So when the oldest instruction is ready to be retired, is detected to have caused an exception, the control logic checks for several things. So oldest instruction is the oldest instruction in the machine at this point, basically. You don't do this for a later instruction. So first of all, you ensure that the architectural state is precise, register file, program counter, and memory. If you write to these in order, then no problem. You flush all younger instructions in the pipeline, very similar to the flush that we saw in the pipelining. You flush everything else in the pipeline except for this instruction. And then you save the program counter of this instruction and the registers as specified by the ISA to some location in memory so that you can reload them back. This is called the context of the program or context of the thread. You save it so that you can reload it when you restart this program. And finally, the pipeline controller, this control logic basically that I mentioned over here, redirects the fetch engine to the appropriate exception handling routine. So if the exception happened because of an overflow, it basically has a code. The code says this is an overflow exception, and this code is associated with the program counter of an exception handling routine This is where the exception handling routine starts. And basically, the program counter is set to that address where the exception handling routine starts. And this, basically, the processor starts executing that exception handling routine from that location that's associated with the overflow. If this was, I don't know, a general protection exception, you're trying to access some location that you're not supposed to access, there's another exception handling routine. If this was an undefined instruction, there's another exception handling routine. So basically, there are different exception handling routines for different exceptions that are executed depending on the exception that happened. Hopefully that makes sense. And it's very specific to the exception in the end, right? Basically, the exception handling routine executes. In the end, it figures out whether it can successfully return to the program. If it can successfully return to the program, what it does is it knows the program counter because it was saved. It knows the registers because it was saved. It basically writes to the program counter and reloads the registers as with the saved registers. And then you're back to executing the prior program that you kicked out because you need to handle the exception handling routine. So it all works out. Again, there's no magic here. The key is that exception handling routine in the end decides whether you can actually restart the program by reloading the PC and the registers that were saved or not. For example, with an undefined instruction, you may not be able to restart. If the program tried to execute an undefined instruction, you may not be able to go back to the program unless the programmer knows something. As I said, the programmer can supply these exception handling routines as well. So interrupts are actually exactly the same, except these are interrupt handling routines, basically. You need to change this to have caused an exception to something else. Whenever an interrupt comes and whenever you decide to handle it, you still need to do these things because it's not associated. Interrupt is not associated with an instruction, right? As we said, it's an external event. Okay. So just to show you, actually, this is from the x86 ISA manual, which is a clearly real thing, and it's actually beautiful. This is, in my opinion, some of the best description that I've seen in terms of interrupts and exceptions. Yeah, I'd recommend you take a look at it. But let's read it actually, because I think it's always good to see the real systems, how they talk about this. It's nothing different from what I said. When an interrupt is received or an exception is detected, the currently running procedure or task is suspended while the processor executes an interrupt or exception handler. When the execution of the handler is complete, the processor resumes execution of the interrupted procedure or task. The resumption of the interrupted procedure or task happens without loss of program continuity. That's what precise exceptions means. Unless recovery from an exception was not possible or interrupt caused the currently running program to be terminated. So everything I said actually boils down to this description. Power failure may terminate your program, for example, or a machine check exception may terminate your program. But otherwise, you go back to your program. Okay, I'd recommend reading this entire thing on your own because it's actually nice. So before we go on further, let's talk a little bit more about why do we want precise exceptions. Clearly, the legalistic answer is von Neumann model demands it. Right? If you're designing a von Neumann system, you'd better do it. Obey the contract. Yes, correct. That's very legalistic, though, right? In a sense, there's less insight in this answer. The insight is why does the von Neumann model demand it? Right? You should ask the next question, basically. Yeah, the law specifies it, but is the law good or is the law correct? That's critical thinking, basically. Why did the von Neumann model specify it? Well, remember the data flow. Data flow actually doesn't specify it. That's another law. That's another contract, basically. Why? Because basically the main reason is it aids software debugging. All right. That's the main benefit of von Neumann architecture also. As I said, if you actually don't have this notion of precise state, it becomes very difficult to figure out what happened in the program. It may be that 5 instructions after the exception causing instruction wrote to the register file. It may be that 10 instructions wrote to the register file. It may be that 25 instructions wrote to the register file. It may be that none of them wrote to the register file. It may even be that some prior instructions did not even write to the register file, right? If you actually don't satisfy this precise exception requirement, you basically are at a loss of exactly what happened. Whereas precise exception basically clearly dictates what should happen and what you should expect to happen. Right? It's all about basically the expectation and whether the reality matches the expectation. That's why von Neumann model is very helpful in debugging, whereas data flow is not helpful because data flow by nature says Okay, I'm not going to tell you what happened. Basically, there's no way you can look at a machine and tell exactly what happened easily. Okay, so basically it adds software debugging. It enables easy recovery from exceptions. So let's go back to this picture, what I said. You basically need to do all of these steps, flush all the younger instructions are in the pipeline, save PC and registers, execute the exception handler, and then to restart or recover, you load the PC and the registers back. That's it. That's the idea, basically. It's very simple. Think about it from a data flow perspective. It's actually very, very difficult to do this recovery. Enables easily restartable processes. Basically, it's very similar to what I just said. There are some other issues over here, but because we don't have a whole lot of time, I'm not going to discuss it. Okay. It enables traps into software. So this is actually very interesting also. So for example, software may have some unimplemented opcodes. Or your machine may have some unimplemented opcodes, but it may be implemented by the programmer. So the programmer basically, or some binary translator. We discussed binary translation, right? So basically, you use an opcode in your program. It's not implemented by the hardware. It could be a multiply instruction, let's say. Multiply is not implemented by the hardware, but you actually use an opcode, and that specifies a multiply. When you get to it, the machine basically takes an exception saying, I don't know this instruction, I don't recognize it. So go to this exception handler that's supplied by the virtual machine or the programmer. And that exception handler implements the multiply instruction using the instructions in the machine that is supported by the hardware. So this is how it's actually very powerful. You can actually have a program that contains these software implemented instructions that are not supported by the hardware. That's the idea. Okay, so let's take a look at how we ensure precise exceptions in a single cycle and multi-cycle machine first, and then we're going to talk about pipelining a little bit more. So this is very easy to do in single cycle and multi-cycle machines. Single cycle instruction binaries are cycle boundaries anyway. So whenever you actually finish an instruction, you know that you finished that instruction and you didn't start any instruction after this, and all of the prior instructions are finished. That's the beauty of a single cycle machine, right? Multi-cycle machine, it's a little bit different, but easier basically than pipeline machines, especially with multi-cycle execute. But basically, you add special states in the control finite state machine that we have seen that lead to the exception or interrupt handlers. I'm going to show the picture of this. And then you switch to the handler only at a precise state, meaning before fetching the next instruction. Remember that we had the finite state machine where there's a fetch state and then decode, and then you basically execute an instruction, and then you go back to the fetch state. You'd better switch to the handler before you fetch the next instruction, not in the middle of the instruction execution. That's the idea, basically. So this is from your book, from your readings. Your book basically shows that it basically shows implementing two exceptions, overflow exception, and I believe there's an undefined instruction exception. And you need basically support in your data path. This is the multi-cycle processor that we have seen. You basically need support in your data path so that you can record the cause of the exception. So there's a cause register, for example, over here. Whenever an exception happens, this cause register is loaded with the cause of the exception. In this case, there are two of them, as I said. It could be an undefined instruction. It could be an overflow in an integer operation. And you also save the PC program counter. Basically, this is the exception causing program counter so that you can actually put it somewhere. And then you need support for starting the exception handler. So there's a single exception handler in this particular case. Exception handler starts at this address. Whenever you basically find that there's an exception or interrupt, unfortunately, your book actually kind of mixes these. Fine. Basically, what you do is using the support that's provided in the data path, the machine saves the cause of the interrupt, basically two different encodings, saves the exception causing program counter, which program counter caused this problem exception, and sets the program counter to the exception handler's address, as you can see over here. So this is the program counter mux, if you remember. We are extending it with this special address, exception handling routine's address. And when an exception happens, that exception handling routine's address gets loaded to the program counter. And in that exception handling routine, what happens is you check what is the cause, and depending on the cause, you may jump to some other part, some other routine, basically, some other method, basically. Okay, so hopefully this is clear. It's not that hard to add the support, but of course you need to have the support in the finite state machine as well. Basically, you can see over here. Okay, let's take a look at a couple of them. If the opcode is undefined, meaning others, that's your book's terminology, you get an undefined opcode and you have an exceptional condition over here, and then you basically set the exception register with the appropriate cause, write the exception program counter, whatever program counter was executing at the decode stage over here, and then change the PC source, program counter source, so that the exception handler routines program counter is loaded to the program counter, so that you can actually start the exception handling routine at this point. Another exception happens in overflow. So you can see this is ALU operation, executes. If there is no overflow, no problem, you continue as normal. If there's an overflow, you go basically right to the exception PC, you write the cause as overflow code, and you change the program counter to the exception handling routines address. So basically, it's very similar. You need to add these additional states that prepare the processor to jump to the exception handler at appropriate places whenever you detect an exception in a multi-cycle machine. So hopefully this is relatively simple. It's very similar to adding another instruction, except you're not adding another instruction, you're adding another way of jumping to some exception handling routine. There's also another thing. I would recommend reading your book, actually. MFC0 instruction, MIPS, is used to copy the exception handler cause into a general purpose register. So you can actually operate on these registers. So basically, the exception cause can be put into a register in the general purpose register. So let's read this actually relatively quickly also. In summary, an exception causes the processor to jump to the exception handler. The exception handler saves registers on the stack, then uses MFC0 to look at the cause and respond accordingly. When the handler is finished, it restores the registers from the stack, copies the return address, blah, blah, blah. So there's some things that the system needs to do to make sure the exception handler works correctly. Okay, but this is single cycle, multi-cycle. Pipelining actually adds more complication, because single cycle, multi-cycle, it's nice to determine the precise state. But if you're presented with a picture that looks like this, how do you make sure you know what the precise state is? Okay, so let's take a look at a solution that doesn't really work very well. So this could be one. So this is wrong, as we discussed, right? You should not write to this architectural state out of order. Okay, you say, I'm going to make sure each operation takes the same amount of time. Divide 60 cycles, add operation 1 cycle. Yes, I can finish it in 1 cycle, but I have this nuisance of precise exceptions. So I'm going to make sure that that also takes 60 cycles. You can now see the problem with it. This solves the problem. Yes, this solves the problem of precise exceptions. But unfortunately, there's a big downside. Now, worst case instruction latency determines all instructions latency. You cannot actually finish some instructions early and let's say, don't worry about them. So memory operations could take, for example, 500 cycles, right? Or some memory operations may take 1,000 cycles, right? So where do you stop here? How long should your pipeline be? Should it really be 1,000 cycles to make sure that your precise exceptions are kind of nice and every instruction writes to the register file in order? Yeah, this is not a viable solution because of this, basically. You don't want to lengthen the pipeline. You want to let each instruction take as long as it takes while obeying the precise exception semantics. Yeah, this is what I said earlier. Okay, so there are multiple solutions proposed to this problem. We're going to talk about one solution, which is the reorder buffer. There are actually a lot of interesting solutions: history buffer, future register file checkpointing. We're not going to talk about them in this lecture. They're in backup slides, and you can actually look at some readings. One of your readings actually talks about them briefly. But in existing systems, actually, reorder buffer is very heavily used. These two other ideas are also very heavily used. History buffer is not as much used today. But we may actually go back, when we talk about out-of-order execution, we're going to talk about future register file a little bit, because you need it in out-of-order execution, actually. So let me give you the basic idea of the reorder buffer, and then we're going to take a break. So as I said, we will not cover these. So the basic idea is actually very similar, very simple, let's say. We want to complete instructions out of order, meaning execution happens as long as each instruction takes. One instruction may take 60 cycles, another may take 8 cycles, another may take 1 cycle. Each instruction finishes in however long its execution unit takes to finish the instruction. and produce its result. But we don't write the result to the architectural register file until that instruction becomes the oldest in the machine, meaning we need to buffer those results somewhere. That's the idea over here. So we can take those results and forward them to later instructions. So later instructions can make progress, but we don't write them to the register file. We don't expose them to the architectural state, basically. That's the idea. So in other words, you're reordering the instructions. You're completing the instructions out of order, but when you're updating the register file in memory, you're doing that in sequential order. But to be able to do that, when you complete the instructions, you need to buffer their values so that those values are visible to dependent instructions later. And also, those values are written to the architectural state when they're supposed to be written in sequential order. Okay, let's take a look at this picture now. So this is our picture, actually. Okay, I don't know why this is not moving here. This is our pipeline. You have different functional units that take different latencies. They produce their results, and they write their results to the reorder buffer first, which buffers the results. And then you update the architectural register file only when the instruction that produced the result is the oldest in the machine. So in sequential order, you update the architectural register file. But the production of the results happen internally, and they're written into the reorder buffer. So the reorder buffer really buffers the results of the instructions. And also, it keeps track of the sequence of instructions. Basically, it's implemented a circular queue in hardware, which keeps track of the oldest instruction and the youngest instruction, all instructions in between in sequential order. And it knows exactly when an instruction becomes oldest. When an instruction becomes oldest, its result is written into the register file, which is the architectural state. So hopefully that's clear. Let me give you the process quickly. So when instructions are still decoded in order. When an instruction is decoded, it reserves the next sequential entry in the reorder buffer. It basically writes its information into the reorder buffer, saying, this is the instruction. I'm going to produce this destination register ID, for example. When it completes, it writes the result into the reorder buffer entry. This destination register ID, I produce the result, let's say value 500 for this destination register ID, and writes into the reorder buffer. And reorder buffer keeps checking the oldest instruction in the reorder buffer. When an instruction is the oldest in the reorder buffer and is completed without exceptions, its result is moved to the register file or memory. We're not going to talk about memory as much, but it's very similar. So basically, reorder buffer every cycle checks what is the oldest instruction in the machine, and then looks at that entry of the oldest instruction. Did it cause an exception? If it caused an exception, it basically does what we discussed. It jumps into the exception handler, as we discussed. If it did not cause an exception, then it basically says, oh, did this instruction finish? Yes, the instruction finished. And here is its destination register ID in the entry in the reorder buffer. And here's its result. And what the reorder buffer logic over here does is takes the destination register ID, takes the result, and updates the register file's destination register ID with that result. That's the idea. And as a result, you do this update of the register file sequentially in program order. Does that make sense? Okay, good. So memory is very similar. We're going to talk about memory later on, but now let's take a break. So I went a little bit further. So let's take a 10-minute break. So 2 minutes after the bell, we're going to go into reorder buffer a little bit more. Okay. Let me see.
For this lecture, right?
Yeah, for this lecture. Yeah, because I may need to use it, but I don't know. Let's see. So let's try it, actually. I think I went slower than I expected. So let's see how we can use the doccam. So let me. No, I think tablet I know. I need to log into Zoom here, but.
If you stop screen sharing.
Okay, let's stop screen sharing. All right. Nice. Okay. So let's continue. So, oh, is this wrong? Okay.
So this is your screen sharing. You can switch between those two.
Okay.
This is screen sharing in two.
Okay.
And both your
Oh, I need
devices-
screen. Okay. Okay. I see. Whenever I need it. Thanks. Okay. Now that we've introduced the concept of reorder buffer, hopefully this is conceptually simple, right? The concept is very simple in a sense. You reorder the instruction. Basically, you keep track of all of the instructions that are decoded, but not yet finished. Finished meaning not yet updated the architectural register file. And you make sure that the architectural register file updates are done in sequential order. That's the purpose of the reorder buffer. And just to repeat this, just to hammer it home, let's say, when instruction is decoded, it gets allocated the next sequential entry in the reorder buffer. But this is a circular queue in hardware. So it's the next sequential entry in the circular queue. When the instruction completes, finishes execution in the functional unit, it writes its result into the reorder buffer entry. Now, later instructions can get that result from the reorder buffer, but the instruction doesn't write to the register file. Now, when the instruction becomes the oldest in the reorder buffer and is completed without exceptions, its result is moved from the reorder buffer to the register file or memory. That's the idea. And this process is done completely sequentially, meaning in sequential order. So you can produce your result and write into the reorder buffer out of order, out of the program order. But updates from the reorder buffer to the register file, architectural state is done in sequential program order, preserving the von Neumann semantics. So whenever you look at the register file is always updated in the program sequence, program order, basically. Okay, now let's take a look at how do we implement it, because this is a very powerful idea. It has multiple benefits, as we will see, but it also complicates the machine. Now we're going to complicate the machine. Just to reiterate what it looks like, we're looking at a hardware structure that keeps information about all instructions that are decoded. Decoding happens in sequential order, but not yet retired or committed. Retirement happens also in sequential order. So there's a part of the machine in between that is not in sequential order. And this is what the reorder buffer looks like. As I said, it's a circular queue in hardware. You have some number of entries. It could be 16 entries. Existing systems actually have hundreds of entries. And one of you have two pointers. One pointer is to the oldest instruction. This is the pointer to the reorder buffer entry that contains information about the oldest instruction in the machine that does not update the architectural register state clearly. And another pointer points to the youngest instruction, or the next instruction to allocate, let's say. So in this particular case, some part of the reorder buffer is empty, let's say, it's not allocated. Okay, so it's basically a data structure implemented in hardware. And it has some entries. Each entry has some fields. So let's take a look at some of the fields, basically. So entry valid means that whether you have an instruction that's associated to that entry that's allocated. So if this valid bit is 0, there's no instruction in this reorder buffer entry. If it's 1, an instruction was decoded and placed into this reorder buffer entry. Destination register ID is the destination register ID that this instruction is supposed to be writing to when it's going to update the architectural register file. Destination register value is the value that it's going to write to the destination register ID. And destination register written question mark, meaning whether the destination register value has been produced. This says that instruction, if this is set to 1, this means that the value here is actually trustworthy, meaning the instruction finished execution, it wrote its result into its entry, and the value is here ready to be written to the register file whenever the time comes. If this bit is 0 over here, that means that this value is not ready yet. The instruction didn't finish execution yet. This basically tells you whether this value is ready or not, available or not in the reorder buffer. Right? These are the 4 major important parts of a reorder buffer entry that we're going to use. So every instruction, basically, whenever it's allocated in the reorder buffer, sets the valid bit entry, valid entry. If there's no, basically, you first need to check, of course, if the reorder buffer is full. Whenever you're decoding an instruction, the first thing you need to check is whether the reorder buffer is full. If the reorder buffer is full, the machine needs to stall because there's no reorder buffer entry to place this instruction. And reorder buffer is full if all of the entries are valid, of course, right? If one entry is invalid, then the instruction gets decoded and placed into the reorder buffer, entry becomes valid. Whenever the instruction gets recorded, destination register ID is written. Value is not available yet, and destination register written question mark is set to 0 because destination register is not available yet. Whenever instruction finishes execution, it knows its reorder buffer entry ID because it's allocated it in the decode stage. It carries it with it in the pipeline. So this becomes associated with the instruction in the pipeline registers. When the instruction produces its result at the end of the functional unit execution, it updates its own entry, let's say entry 1, with the destination register value and sets this bit to 1, saying that its destination register is available. Now, a later instruction, if it needs that value, can get it from the reorder buffer, right? If a later instruction comes in, it can basically check the reorder buffer and get the value. We'll see that. That complicates things. Okay, does this make sense? Now we're going to complicate this a little bit. So this is what's really is, actually there's more, but I'm not going to use all of them. So store instructions, for example, have a store address, store data. You need the program counter of the instruction because if the instruction calls an exception, this is your exception program counter, for example. You need some other valid bits for register data, some other control bits. So I didn't show the, for example, destination register written question mark bit. That's a valid bit for the destination register here. And then there's some exception field saying whether the instruction calls an exception and what kind of exception it caused. So the reorder buffer entry is actually a big entry that keeps track of the state of the instruction, all kinds of status that's going to be important by the time the instruction finishes, and also the data values that are going to be produced by the instruction and what addresses in the register file or memory are going to be updated, plus other stuff that need to be preserved or kept with the instruction so that in case there's an exception, you save that, which is the program counter of the instruction, for example. And this valid bit is the global valid bit saying this reorder buffer entry is allocated to a particular instruction. Okay, so it's actually more complicated than what we're going to really deal with here. Right? To simplify, we actually have don't show all of these different fields. So basically, the key takeaway is you need everything that's required to correctly reorder instructions back into the program order. That's the sequential order. Update the architectural state with the instruction's result or results if the instruction can retire or commit without any issues, exceptions, in other words, or there are no interrupts that you're going to handle before this instruction. And also handle an exception and interrupt precisely if an exception or interrupt needs to be handled before retiring or committing this instruction. So these are the things that you need to have in your reorder buffer entry so that you can actually correctly execute the program in von Neumann semantics. Okay, so you need to have valid bits to keep track of readiness of the results and find out if the instruction has complete execution. These are basically these valid bits. And in our simplified example, that valid bit is destination register written bit, whether the instruction has actually already written to the destination register. Okay, now let's take a look at an example. So with reorder buffer, this is what happens, basically. This is our earlier program. Instead of taking all instructions the same amount of time, we add another pipeline stage. After the instruction finishes execution, it writes its results into the reorder buffer. And this result gets written to the register file when an instruction is ready to commit, meaning when it's the oldest instruction in the machine. So remember, this is the divide instruction. This is the add instruction. This is another divide add. Now, what we do is these independent add instructions can be in the pipeline, can execute, can produce their result, write their result into the reorder buffer in this pipeline stage, but they cannot update the architectural state. Now we've satisfied the properties of a von Neumann machine, sequential, precise exception semantics, right? By adding a reorder buffer stage where we write the results, we get the benefit of instruction executing with the amount of time it needs to execute, not with the worst case instruction execution latency. But we also get the benefit of precise exceptions because that result doesn't get exposed to the architectural state when the result is produced. That result gets exposed to the architectural state when this instruction becomes the oldest in the machine. So you can see that these writebacks into the architectural register file are done in program order. So that's the beautiful sequential model, as we can see. but the results are produced early. Now, it may not be the appropriate question in this particular example, but this results, if somebody needs it, if some other instruction needs it, it can get it from the reorder buffer. So it can basically speed up the execution of the program this way. So for example, if this instruction was dependent on this instruction, it could get it from the reorder buffer or the bypass path. If this instruction was dependent, it could get it from the reorder buffer. If this instruction was dependent on this instruction, it could get the source value from the reorder buffer, right? So we enable the execution of dependent instructions. We don't delay them, but we need to add additional complexity to enable that, as we will see. Okay, so the picture is not fixed, right? This obeys the von Neumann model. Hopefully, you've convinced yourself. But we added some more complexity, which is the reorder buffer stage over here. And if you really want to do what I said, and I think you really want to do what I said, meaning later instructions should get the values in the reorder buffer if they need them, then you need to add even more complexity. And we will see that. So that's basically what we're going to deal with right now. What if a later instruction needs a value in the reorder buffer? One option is to stall the operation, stall the pipeline. That's kind of a waste of time, right? Because the value exists. It's in the machine. It's in the reorder buffer. If you stall the pipeline for an instruction that's dependent on that value, then you're basically wasting a lot of performance. Because you wouldn't do that, for example, with bypass paths, right? We added all of those bypass paths so that we can supply the value to the dependent instruction very quickly, right? Right now, we actually have the value in the reorder buffer. Why don't you just get it over there? So this option is very bad in terms of performance. So the better option is read the value from the reorder buffer. But then this brings the question, how? How do you read a value in the reorder buffer? The way we discussed, the reorder buffer is implemented. That'll lead to some complications. So that'll lead to this picture, basically. So a register value can be in the register file, or the reorder buffer, or in the bypass paths, forwarding paths. So there are three places where a register value can come from in a machine. When you decode the instruction, well, bypass paths I just added over here also. When you decode the instruction, you access all of them concurrently. So register file, we know how to access it, right? It's called random access memory. You index the register file with the register ID. It's very similar to the memories that we have seen earlier, which is the address of the entry. Okay. So we know how to do this. But the value may not be in the register file. Why? Because this instruction is going to write to the register file, but it hasn't written yet. So basically, first of all, we need to figure that out first. We need to actually add a little bit more complexity to the register file also, as we will see. This instruction is writing register 3, for example, but it hasn't written its result yet. So where's the value? Well, it may be nowhere, meaning the instruction is not executed yet. It's finished its result yet. So it may be in the functional units. After the instruction actually finishes, produces its value, it can be forwarded by the bypass paths. After the instruction writes its result into the reorder buffer, the value is in the reorder buffer. But now, how do you access that value in the reorder buffer? Because you cannot just access the reorder buffer by saying, oh, I want register 3, right? That's not the structure of the reorder buffer that we have seen. Let's go back to the structure of the reorder buffer. The purpose of the reorder buffer is really order the instructions. As a result, it's really a circular ordered queue, right? As I said, it's a circular ordered queue. So you access it with the entry ID. You don't access it with the destination register ID. So now we're going to introduce a new memory structure here so that we can get the destination register ID we want. Okay? Let's take a look at this. Okay. So basically, you want register 3. We're going to ask the reorder buffer, reorder buffer, can you give me register 3's value? Okay, actually, you tell the reorder buffer, I'm instruction 56 in the reorder buffer. I want the register 3 value that is produced by an earlier instruction that's closest to me. Can you give it to me? So now this is a more complicated search, because there may be multiple instructions in the reorder buffer that actually write to register 3. Some of them have finished, some of them did not finish. You want the latest instruction that wrote to the register 3 that is just before this instruction, of course, right? That's the idea. So this is actually a very complicated search. It's called content addressable memory, because the reorder buffer is not organized based on the register IDs. It's organized based on the entry IDs, which is the instruction number, let's say, as it's allocated. So you need to search this reorder buffer with the register ID, which is really part of the content of an entry. That's why it's called content addressable memory. And we will see that this is quite expensive, actually. Okay, so let's take a look at a reorder buffer example. To be able to do this example, we also need to look at the register file. So now we actually have two places where the value comes from. Ignore the bypass paths for now, forwarding paths. We've already kind of seen them. You just need to incorporate them into the structure. But the value can come from the register file or the reorder buffer. How do you know where the value comes from? Well, if the value is written into the register file, latest definition of a register is written into the register file, this val bit should be set. So we're going to add val bits into the register file saying whether the value is valid, meaning whether the value is updated by an instruction in the register file. Okay. So this value in the register file is valid if the instruction, if there's no instruction in the machine that is writing to the register, that register. If the oldest instruction in the machine that's writing to that register has finished and updated the value, and clearly there's no instruction in the machine that's writing to that register. Well, that's the case where this value is valid. In all other cases, there's some instruction that's going to write to that register. It hasn't written to the register file yet. As a result, this valid bit is 0. As a result, you cannot trust this value. In that case, you search the reorder buffer. So let's take a look at how we search the reorder buffer. So reorder buffer has oldest instruction. The Angular instruction, you basically need to look at all of the entries in between that are older than this particular instruction so that you can get that value. Okay, so initially all registers are valid in the register file and the reorder buffer is empty. And this is an example thing that we will simulate, but I will also assume some things. I will also assume that there are some instructions in between. So let's now switch to the simulation of this reorder buffer example. Okay, let's see how we can switch before we go into the next thing. So what do? DocuCam over here, and we're going to stop sharing this one. Okay, otherwise I'm going to use the board. Okay, now you can see that. Okay. I assume people on Zoom can see as well, right? Can you see this without any problems? Okay. Okay, so let's take a look at it. I could do it in 3 different modes actually. Here, on the board, or my iPad, or even here actually, annotating, but that's very cumbersome. So I'll use it, let's say, in the not most up-to-date technological mode. Okay, so basically, initially what you have is when you start the program, all registers are valid. So these are 1. And you have real values over here that I'm not going to populate over here. And initially, all the reorder buffer entries are invalid. I'm not going to show that over here right now so that I don't waste each, let's say. Initially, all invalid. Now, let's take a look at what happens. Actually, let's simulate this program. Multiply instruction gets decoded. So we're going to decode this multiply. Hopefully people are seeing it. What does this mean to decode the multiply instruction? Multiply instruction reads register 1 and register 2 first. Register 1 is valid, great. Register 1 is valid, great. Let's assume that its value is 1. Register is also valid. Let's assume that its value is 2. So now multiply takes value 1 and value 2. That's good. It's valid because that means that you can trust the value in the register file. Now it's going to write to register 3. Now what multiply does is, multiply sets register's valid bit to 0, saying that you cannot trust the value over here because I'm going to write to it. And any later instruction that comes after this multiply should not get this value because there's multiply that's going to produce that value, right? So it sets the valid bit to 0 for register 3. At the same time, multiply gets allocated to the first entry. Let's assume that the reorder buffer is empty initially. So multiply allocates entry 0, makes the entry valid, writes its destination register ID, which is 3. Remember, that's the destination register ID. The destination register value is not available yet because multiply didn't execute. Destination register written? No, it's not written because multiply did not execute. And it also writes a bunch of other stuff that we're going to ignore for now. Yes. Oh, because I'm assuming that this initial condition, right? All registers are valid in the register file and the reorder buffer is empty. That's the reason. That's what happens when you start the machine, right? Somebody loads the register file. Makes sense? That's the assumption. You mean why is this valid already? Or these registers? Oh, this val bit basically says whether the entry is allocated. Yeah. So everything else is 0 over here. So I assume those are all zeros basically. Reorder buffer is empty. Okay. So that's the multiply. Now multiply is going to take its sweet time. Let's say 60 cycles. I don't know, to execute. Okay. So the second multiply comes in. It's going to source register 3. I don't know, maybe 60 cycles. Maybe we don't need that information, but the second multiply comes in. So it basically looks at R3 and R4, right? R3 is not valid. Okay, so I cannot get the value from here. R4 is valid. Let's assume that it's 4. So I get 4 over here in the next cycle this is happening. R3, where should I get R3 from? Well, the way to determine it is actually you search the reorder buffer basically. And in this particular case, it's not going to be able to get the value, but in some other case, it may be able to get the value. So what the logic that you will need to add over here is to search the reorder buffer. So how do you search the reorder buffer? You're looking for register 3, right? So it's clearly not in the register file. So it may be in the reorder buffer. So I'm going to search the reorder buffer. So how do I search the reorder buffer? I take the source register, compare it to every single entry over here. Is it equal? Okay. And then there's another entry over here. Is R3 equal to that? And I keep doing that. So basically, I have comparators, 16 comparators in this particular case, that check whether this input R3 source register is equal to the destination register ID in the reorder buffer entry. And if it's equal, that could potentially supply the value. But that's not enough, because this multiply is actually you need to consider only the instructions that are prior to you, meaning the valid ones, right? So basically, you need to search the reorder buffer, find R3, and also check the valid bit. And you also need to find the closest instruction to you that writes to R3. Okay. So in this particular case, because the instructions are too close to each other, this R3 is not in there produced yet. So what this multiply is going to do is wait until this value is produced and written into the reorder buffer, and basically will get the value from the bypass path or the reorder buffer, but we're ignoring the bypass path for now. It will get the value from the reorder buffer when the instruction actually writes the value there. Does that make sense? So basically, this is the content addressable memory. It's called CAM, content addressable memory. You're searching the reorder buffer with the content in each entry. So you're looking for R3, and you're looking for the latest definition of R3 in this particular case. Then multiply is going to stall until it gets that value. Okay, let's execute this a little bit more basically. So this multiply sets R11, R11 is not here, sorry. R11 becomes invalid. And when multiply allocates its entry over here, maybe I should use some other color over here right now. Yeah, this multiply gets allocated over here. It's going to write to R11. Its value is not available yet. This is invalid, 0, in other words, and there's some other stuff. Now let's take the other add in here. So this next add comes. It's checking R5 and R6. They're both valid. That's good. 5, 6, and at some point it executes. Let's say so basically it can get the values 5, 6 over here. Now it's going to write to R3. Okay, there's something interesting that's going to happen, right? It doesn't need any of the earlier values, so it can actually execute. So it's going to make its entry 1 over here. And it's going to check, set the reorder buffer destination register ID of its reorder buffer entry to 3. Its value is not available yet, and as a result, the destination register written is 0, and there's some other stuff. Now we basically have 2 instructions that are writing to register 3, and this is the youngest one. So of course you need to keep incrementing the youngest one, right, as well. So if a later instruction comes, which is the whole point of this example, actually. Okay, let me find another color. I don't know. Later instruction, this add R3, R8. So because this is the prior instruction, this third instruction is writing R3. R3 is still 0, right? Okay. We don't know the value. So if a later instruction comes, they need to search the reorder buffer. So a later instruction comes, it's sourcing R3 and R8. R8 is no problem. It's valid. And the value is 8, let's say. It gets 8 over here. R3, which R3 should it get? Well, there are two definitions of R3s over here, right? There are two prior instructions that are going to write to R3. So when this add is being decoded, when this last add is being decoded, it needs to search the reorder buffer and find the latest definition of R3, meaning it should get the value from this reorder buffer entry when it becomes available, of course, right? If the value was available at this point, then it would get it right away, of course. Does that make sense? So basically, the whole point of this example is to show you that there could be multiple definitions of R3. There could be actually 16 R3s over here, right? All instructions may be writing to R3. Maybe that's not great from a semantic perspective. That's possible. Nobody forbids that. But basically, there could be multiple R3s. Whenever an instruction gets decoded, it should get the value from the R3, the latest definition of R3 that's older than this instruction. So basically, there are a bunch of instructions that are in the machine that are writing to registers. You should get the value that you need from the latest definition of that register. And to be able to do that, you need to have this content addressable memory. So what does this look like? Basically, every entry has a comparator that looks like this. So basically, there are 16 comparators. You also need to check the valid bits. For all valid locations, you compare the source register to the destination register ID of that entry for all valid locations. And you need to get the latest one, meaning this is a prioritized. It's a prioritized search. You do a content addressable search that's prioritized based on the closeness of the instruction, meaning the latest instruction. You need to get the value from the latest definition of R3. So in hardware, you can think about how to do this. It's actually a priority-based, let's say, muxing. You can divide in multiple ways. You can actually implement in multiple ways. But this search is not just a content addressable search, but it's also a prioritized content addressable search. Does that make sense? That's what this makes this, what makes this complicated, actually. It's not easy to implement this. 16 entries, 16 comparators. 500 entries, 500 comparators. It's not just one comparator. You need to do it for both sources because both of your sources may be invalid in the register file. So now you're up to 1,000 comparators, right? So the complexity actually grows linearly with the number of entries in your reorder buffer. And the complexity is not just a simple search, it's actually a prioritized age-based search base. Is this clear? Okay, so there's one more thing that I should actually say over here. Now what we've done actually is something even more deeper than you may realize, which is really the soul of out-of-order execution. I'll handle your question very quickly. So now R3 is here. There's one definition of R3 here. That's just multiply. It's in reorder buffer entry 0, right? The second dependent instruction should get its value from reorder buffer entry 0. So we've linked this instruction, we linked this producer to this consumer. There's another R3 over here, which is produced by entry 3. This is actually rob entry 3. And the later instruction, rob entry 4, is going to get that value. So we've linked this instruction, this producer instruction, to this consumer instruction. So now we have multiple definitions of R3. Remember the dependencies, output dependencies, false dependencies? We actually can have many, many registers inside the reorder buffer. If you actually have 1,000 entries in your reorder buffer, you may have 1,000 definitions of R3. If all instructions are writing to R3, basically they're all producing the value of R3 over here, different values, of course. And it can actually correctly connect it to the dependent instructions that source the R3. So that's the idea over here. This is called register renaming. I'm going to talk about that in a little bit as well. Yes, do you still have the question or is this gone? Okay, register renaming solves a lot of problems. Okay, so keep this in mind. Basically, we've kind of renamed R3. Now R3 is not here, right? This is our register file, architecture register file. We said architecture register file doesn't have R3. It's invalid. R3 may be anywhere here. And actually, there could be many places. This is the notion of renaming, register renaming. And this is going to be very fundamental to when we discuss out-of-order execution in the next week. That way, you can eliminate false dependencies. So basically, true dependencies still remain, meaning you basically connect the producer to the consumer. But false dependencies don't remain because you basically have multiple definitions of RT and you connect the correct producer to the correct consumer. That's the idea. So we're going to see more sophisticated examples of this in the next lecture. Okay, now let me go back to sharing my screen over here. Okay, and then we still need to do this. Good. Okay, so that was our reorder buffer basically. Now you can say that, oh, this content addressable logic is expensive, and you're absolutely right. So we're going to fix that. So there's another way of doing things. Basically, let's simplify the reorder buffer access. The idea is to use indirection. And the idea is to access the register file first, check the register is valid when you're decoding an instruction, when you want to actually figure out what the source values are. Access the register file first, as opposed to accessing them concurrently, right? Here we were accessing them concurrently. I kind of didn't say it exactly, but it's really you access them concurrently. You do a regular register file access here. You do a content addressable memory access here. And if the source is valid over here, you get it from the register file. If it's not invalid, the result of the reorder buffer needs to be provided. Or there could be bypass paths that we kind of ignored, but they should be there also. But this is too complicated, basically. This reorder buffer search is actually very long. It can take very long, this content addressable memory, especially if the reorder buffer size is large. So let's try to simplify it. And the simplification is actually adding indirection, basically. Meaning, access the register file first. If the register file is invalid for the registers you're looking for, then access the reorder buffer. Okay. Now reorder buffer doesn't need to be content addressable. Why? Let's see. Basically, if the register is not valid, the register file stores the ID of the reorder buffer entry that contains the value of the register. So if we go back to what I showed you over here, actually, I'll do that in a little bit. Basically, if the register is not valid, you don't just say, oh, it's not valid, figure it out. You say, the register is not valid, but I know which reorder buffer entry is going to produce this register, because that has gone through me. In the decode stage, this instruction said, set my valid bit to 0, and it was allocated to reorder buffer entry 55. So don't look up me, but look up reorder buffer entry 55, because it's going to produce the value you're looking for. That's the idea. So we basically have an indirection that points the register file, points from the register file to the reorder buffer entry. And that's how you can connect the instructions nicely. Okay, so basically now we've mapped the register to a reorder buffer entry. If there's an in-flight instruction writing to the register, of course, meaning the register is invalid in the register file. Okay, so actually I'll go back to the same example over here. It's not that different. So DocuCam over here, stop sharing over here. Let's see if it works. Basically, it's the same example over here, register file, but instead of in the register file, what we're going to say is we're going to add another thing. We're going to call it tag. This is really the pointer to the reorder buffer entry that's going to write to the register next. That's going to write to the register next. That's going to supply the definition of that register. And when this instruction is decoded, let's look at R3 here. R3 is interesting. When the first instruction is decoded, it makes the register invalid, and it says basically the value is going to come from reorder buffer entry 0, right? When this instruction is decoded, add R5, R6, R3, this is still invalid, but it updates the tag to be 3. Because any later instruction, oh, not 3, sorry, it's 2. Yeah, because this is the instruction that's also writing to register 3. When it gets decoded, it updates the tag saying that I'm going to produce the result in reorder buffer entry 2 over here. So any later instruction can come and pick it up from reorder buffer entry 2, right? They don't need to search the reorder buffer entry in a content addressable manner. I'm going to tell them exactly where I am going to put the result, entry 2. So get it from entry 2. That's the idea. Basically, that's how we get rid of the indirection, right? So let's go back over here again. Something happened. I'll share. Okay. So basically, this is the tag, which is a pointer to the reorder buffer entry. And you can do the exact simulation right now, which we just did. We just need to update the tags such that the definition of R0, you basically, whenever you decode an instruction, you also put the reorder buffer entry of the instruction that's going to write to that register to this tag field in the register file, right? And any later instruction can now come. If it's sourcing R3 and it's invalid, the tag says reorder buffer entry 2. Now, you can use that tag and index it into the reorder buffer. This is address 2, basically. You don't need to search for the content for register 2. Register 3. You just need to index the reorder buffer and figure out what's the thing in address 2. So let me go back over here again. Sorry for this frequent things, but basically this says 2. What do? while decoding this instruction, this latest instruction, you basically take this address to index the reorder buffer, just like a random access memory, meaning not content addressable search, and basically get the value if it's available over there. Otherwise, you'll stall until the value becomes available. Right? Basically, this turns the reorder buffer from a CAM, content addressable memory, into a RAM, which is simpler. At the expense of some indirection, you have to go through the register file first. Right? Okay. No. Okay, so basically, I've given you really the core concepts of the reorder buffer right now. Let's take a look at them a little bit more. So this is actually real. Intel Pentium Pro is actually one of the first processors that have implemented it. And you can see that reorder buffer looks like this. It has some data, and then it has some status, and this is their architectural register file, basically. And they actually made this a little bit simpler in a sense. They also have a map. This is a mapping structure that basically tells where register 0 through register 7 is. Where can you find the value of the register? It's very similar to the tag that we have seen, actually. It's just a different way of looking at it. Basically, register 0 is in reorder buffer entry, I don't know, 5. Register 1, these are the x86 encodings of the registers. Register 1 is in the architectural register file. So you can actually find register 1 and register 1 in architectural register file. Register 2 is reorder buffer entry, I don't know, 55. So basically, we're mapping the architectural register ID to locations in the reorder buffer and the register file. So basically, this is called the register alias table, points to where each register's current value is or will be. Okay, this is very powerful, and we will see this a lot more in the out-of-order execution lectures. Just for your reference, this is Pentium Pro in 1995. This is the first successful out-of-order execution processor of its time. You can see that it's beautiful, right? And because the processor chip couldn't fit the 256 kilobyte level 2 cache, today everything is on chip, they have a separate chip for the cache. So this is the processor and this is the memory. And you have a multi-chip module package here. Okay, so basically, let me go into this a little bit more before we conclude. This is really important. We've renamed the registers with a reorder buffer. As we discussed, output and anti-dependence are not true dependencies because the same register refers to values that have nothing to do with each other, right? And as I discussed earlier, they exist due to the lack of register IDs in the ISA. Now, what we have done is we took the architectural register ID and renamed it to the reorder buffer entry that will hold the register's value. This is also called renaming the architectural register ID to a physical register ID, as we will see later on in out-of-order execution. And after renaming, what you really care about is this reorder buffer ID now. If you got the value from the register file, that's great. You can execute, right? But if you didn't get the register value from the register file, you got a reorder buffer ID, which is a tag. That's what you really care about. You can forget about the architectural registers internally in the machine. You can say, the data I care about is in reorder buffer entry X. And that's what I care about. When it produces the value, I'm going to get it from there. Now your reorder buffer entry can be tens of thousands of instructions, potentially, if you can afford to do that. It's not tied to the instruction set architecture. Internally, you can make the machine extremely big. But instruction set architecture is decoupled from the microarchitecture right now. So that there are a lot of actually really interesting things that happen with register renaming. You're basically freeing the design from a constraint, an architectural constraint. You're making it microarchitectural now with the rename. Okay, this will become even more clear when we discuss out-of-order execution. Basically, you've eliminated anti and output dependencies. Register 3 is not register 3 anymore. Register 3, from your perspective as an instruction, is reorder buffer entry 2 if the value you need is coming from there. It is actually reorder buffer entry 55 if reorder buffer entry 55 is your producer. It's reorder buffer entry 100 if reorder buffer entry 100 is your producer. There may be multiple definitions of architectural register 3, and that's how we've eliminated it. Eliminated those multiple definitions. Okay, there's actually even more deeper things over here that lead to different programming languages, but we're not going to talk about that. But the key is, now we can have the illusion that there are a large number of registers. If you go back to this example, I'm not going to switch back. This example over here, your registers are actually all here in the reorder buffer, right? Your register file only has the updated registers. If it's valid, that's great. But if it's not valid, you have a huge register file over here that's not visible to the architecture. Okay. So just to jog your memory, we've eliminated these anti-dependencies and output dependencies because these register trees are in different locations in the reorder buffer. But of course, you need to obey the flow dependencies by ensuring that you get the correct value from the correct definition of our tree. Okay, so this is for on your own. We're actually going to do this when we talk about out-of-order execution next week. But register file has a pointer to the reorder buffer entry that contains or will contain the value if the register is not valid. And then the question is basically, where is the latest definition of R3 for each instruction below in sequential order? This is actually an easy example. We're going to do a more complicated example next week. And this is for you to actually fill if you're interested. So basically, this completes the picture. Now we have an in-order pipeline with a reorder buffer. We have in-order dispatch or execution. Here, decoding and reorder buffer allocation is done in order. Out-of-order completion of instructions and in-order retirement of instructions. So in the decode, as we discussed, you access the reorder buffer and register file, allocate entry in the reorder buffer, check if instruction can execute. If so, you send the instruction to the execution. This is called dispatch, as we will also see. In execute, instructions can complete out of order. When the instruction completes, it writes its result to the reorder buffer. And retirement happens asynchronously, if you will. There's a state machine that checks whether the oldest instruction has exceptions. If not, its result is written to the architecture register file or memory from the reorder buffer. If there's exceptions, then you flush the pipeline and return, start from the exception handler. And this is a complete machine with precise exceptions. This is really the complete von Neumann machine right now that you can be proud of, if you will, that's pipeline. But of course, this has trade-offs, right? Reorder buffer is not simple. It's conceptually simple, but can eliminate false dependencies is going to be very important for renaming. But it needs to be accessed to get the results that are yet to be written to the register file. So it has either content addressable memory, which is bad, or indirection. In either case, there's increased latency or complexity, but indirection is usually a better way of implementing it because content addressable memory is not scalable. It's expensive. There are other solutions that try to eliminate some of the disadvantages, which we're not going to cover. History buffer, future file checkpointing. As I said in the next lecture, we're going to cover future file a little bit because this is actually very interesting. It's implemented in all modern microprocessors. Checkpointing is also implemented in all modern microprocessors, but we don't have time to cover it. If you're interested, take a look at backup slides, etc. And also some older lectures actually cover this. Okay, that brings me to the end. I will see you, I guess not next week. I keep saying next week, but the week after that, after the break. Have a great break. And yeah, enjoy your time. Yeah, somehow I'm going very slowly in these lectures, but yeah. I mean, you need time to digest these concepts, right?